Okay, now we're going to move out of that one-dimensional kinematics and move into space, or three-dimensional kinematics. Okay, so we've started with position. Okay, and we've defined position before. It's the position is simply just a x in the I direction plus y in the j direction plus z in the k direction, right? That's well defined from statics. Okay, in order to move velocity, we need to take a time derivative of that. Okay, so we take a time derivative of xi plus yj plus zk. Now, when you do that, you have to do it in two pieces, right? Because this is actually a scalar times a vector, the x times I bar, for example. Okay, so we have to do the chain rule where you take the derivative of the first times the second plus the first times the derivative of the second. And that's what I have for the x, y, and z components here, right? So I have dx dt times I plus x times di dt, and then dy dt j, and so on and so forth. The thing is di dt, right, the time derivative of my axes, well, those axes are fixed in our standard rectangular coordinates. Okay, so they do not change with time, therefore the time derivative equals 0. And because of that, all we're left with is basically the time derivative, the velocity in the x, velocity in the y, velocity in j. And again, that's the time derivative of x, time derivative of y, time derivative of z. That is where the x dot, y dot, z dot. If you see a dot over a variable, that means a time derivative, a first order derivative with respect to time. So x dot is the same as dx dt, y dot is dy dt, and z dot is dz dt. Okay, so that's the velocity for rectangular coordinates. Again, fixed coordinate system, so it's just the time derivative in each of the directions. Same thing goes for acceleration. Okay, notice here I've got two dots because it's the second time derivative of the position x. So it's x double dot, y double dot, z double dot, instead of the second order derivative with respect to time. Okay, so that is the most general case for rectangular coordinates kinematics. Okay, now special case, projectiles. Okay, this is a constant acceleration sort of situation because this is occurring in basically gravity, constant acceleration due to gravity. So we can use those constant acceleration equations, right? So we have a projectile that we can launch with some initial velocity. It'll follow this curve, and then based on time, different things, we can figure out what's going on at the end of the projection, the projectile. Okay. Now, in the x direction, the acceleration is actually 0. There is actually no force. I mean, we're going to neglect like drag, air drag. So there is no acceleration in the x direction. So basically, your velocity remains constant. Using this equation up here, plugging in AC equals 0. Okay, the velocity remains constant. The position follows this equation, which is the second equation up here, and this is in the x direction where there's no acceleration. Basically, we're just dropping off the acceleration term in the x direction. So really, I get one useful equation in the horizontal direction. Now, in the vertical direction, these equations apply with the acceleration equals g, and we'll actually have a negative sign because gravity acts downward here on Earth. Okay, so as with before, we have two unknowns we can solve in the vertical direction using these equations, just using negative g for a and plugging in y and vy where it goes. Okay, so recognize that in a projectile problem we can solve up to 3 unknowns, 1 in the horizontal direction and 2 in the vertical directions. And again, this is for the specific case where we have constant acceleration and some projectile moving through a gravitational field. Okay, over on the left side of the screen, these equations apply to anything, and the more general case where acceleration is not constant.